Hey everyone, this is Omoza from Team 5795, back to drawing board, and I'm here to do a video on, as you can see, the mechanics of rotating parts, in this case, gears. So let's get started. Let's start off by discussing what the functions of gears are in any mechanical part, such as for a robot. Gears can be used to invert the direction of rotation with having matching gear connections. They can also be used to alter the speed or the torque of rotational force. This can be used by changing the size of the gear itself. On top of that, they can also be used to alter the axis of rotation, and the best example of this is a worm gear mechanism, which we will show you right now. The mechanism on the left is obviously a gear that's reversing direction, but it is also gears of alternate sizes, which can affect the speed and the torque depending on which gear has the output rotation and which gear has the input rotation. And then on the right, you have the worm gear mechanism, which alters the axis of rotation. As you can see, the axis of rotation can be altered depending on which gear is rotating. In this case, if the circular gear was rotating, then the axis of rotation would be the same as the view of the camera. And if that was true, then the worm gear would be the altered axis of rotation, which is perpendicular to the camera's axis. I talked about gear ratios in the previous slide, and let's go over that a little bit more. What is a gear ratio? Well, it's the ratio between the circumference or diameter of two gears. It could be either because the relationship between those measurements are linear, or it could also be the ratio of teeth from one gear to another, often in the direction of rotation, meaning compared to the input gear to the output gear. So, for example, gears with 10-inch diameter and 2-inch diameter will have a 5-to-1 gear ratio, or gears with 60 teeth to 20 teeth will have a 3-to-1 gear ratio. Now, what does that mean? Well, let's go over that. Here we have some pictures that can be used to demonstrate gear ratios. In the top photo, we have a formula for calculating gear ratios and showing the equality of gear ratios. The gear ratios here are measured by the rotations per minute of the gear times the teeth it has, and you get the values for each gear, derive them, and they should be the same for one gear mechanism. And what this means is a faster rotating gear with less teeth will have the same gear ratio as, or should be equal to the value of the rotations of a slower gear with more teeth. To look at this practically, if you look at the gear labeled in blue and imagine it is rotating at a certain speed, right? It doesn't matter what speed it is, but then it is rotating the gear labeled in red. Now, you can imagine it will take longer for the red gear to finish a rotation compared to the blue gear finishing a rotation. Therefore, it's going to have fewer rotations per minute in the same allotted time. But because it has more teeth, that multiplier compensates for that value. Therefore, you should have the same number on both sides of this equation, or this equality. And gear ratios can be used to multiply forces, which we'll see again in the next slide, but it's demonstrated here in the bottom photo with the Lego gears, which have increasing teeth to from the input to the output gear. As you can see, as all the large gears are connected to smaller gears, which would be rotating faster or completing more rotations while having fewer teeth, and the slower moving gears will be compensating for that by having more teeth. Therefore, the equation will be balanced out. Now let's go on to the next slide to show you what that will look like practically. Now, how are gear ratios used, and what situations do they apply? Well, gear ratios work because they affect the twisting force regardless of the magnitude of the force. The ratio still applies whether it's 5 pounds of torque or 500 pounds of torque. And they can be applied differently on the same object in a car, for example, which has different gear ratios. And let's see that here. You can increase the speed while reducing the torque of the car's output power with a higher gear ratio. And such gear ratios would be used on the highway, for example, where it's more important to go faster than it is to put in a lot of force. Now, on the other hand, you can also increase torque while reducing your speed to lower gear ratios, often gear ratios under 1, which are called overdrive ratios for cars. And such gear ratios will be used on uphill drives where it's more important to have power over speed, or when you first start, when you have to push a car forward from no movement, therefore no added momentum. And in this case, the car can do both because it has a system to apply both forces, which we'll see in the next slide. But this is often the case where if you have a motor that can't output a certain amount of power, you can in fact use gears to output that force. The only issue being is that the force will be a little slower, so you might not want to run a car on a battery meant for a fan, but with enough gears, you could get the same amount of force. It would just be a lot slower. And it works in the opposite direction as well. If you want to get a faster motor or a faster rotation, but your motor can't handle that speed, you can decrease your gear ratio, you can increase your gear ratio to then get that higher speed, although that will be at a loss of torque. Sometimes that's good. Something like an electric screwdriver or a ceiling fan doesn't need that much force, but it needs to go really fast. Same thing with a drill, for example. And gear ratios can apply there, as they will alter the force or the speed as needed, and that's why they're found so commonly in many mechanisms. Now, let me show you what changing gear ratios look like in a car, for example, with the next slide in the picture or diagram. So in this diagram, we can see the gear mechanisms in a car box that output different forces based on whatever gear you set. And as you can see, it's compounding different gear sets that affect the shaft at different times, depending on which is selected. And as you can see, it's not so uniform. It's not one set of gears on the input shaft matched with different gears on the output shaft, which makes sense, right? The output shaft can't be in different locations, so it has to be in the center. Therefore, there's a set total distance you can have between the two shafts. So you change the gear sizes to accommodate and create different output forces, which is a really interesting concept. And this is obviously a simple diagram, but it effectively shows how one single object or one group of mechanisms can employ a set of different gear ratios. Now let's go on to our next slide. Now that you've seen that gear ratios can be used to alter the output force compared to the input force, let's talk about gear trains. You can increase gear ratios and also decrease them by building an array of gears. Now, the total gear ratios can be calculated by multiplying the ratio down the chain of rotation, therefore meaning the input all the way down to the output rotation. So for example, if you have a 5-to-1, 3-to-1, then 2-to-1 set of gears, then that's a total ratio of a 30-to-1 gear ratio. That means that the input to the output speed, it's a multiplier of 30. However, there's an easy way to do it. If you have an array of gears all with the same ratio, you can calculate the total with the formula of the ratio times the to the exponent of the number of gear connections. And you'll see this a little more in the next slide. But the number of gear connections, as you can see below, is imagine having an array of 4 gears with 5-to-1 ratios each. Well, that's 3 connections, right? One connection from the first to second, another connection from the second to third, and then third connection from the third to the fourth gear. Therefore, it's 5 to the power of 3, and then you're left with the following ratio. And to show you what gear trains can look like, let's go on to the next slide real quick. Now here's some image examples of what gear trains can look like. These are obviously just renderings of what would look like in terms of gear radius and therefore general scale of the gear ratios, but it does show you what it works in concept. Obviously, when you have gears in real life, it's going to work a little differently than this. We did see the example of the Lego gears in a previous slide. That is an example of a gear train. And as you can see when we were talking about gear connections, if you look at the photo on the right, you can see that even though there's 2 gears, there's 1 connection. Middle one, there's 3 gears, 2 connections. And then one on the left, 4 gears, there's 3 connections. And so generally it's number of gears you have minus 1 is the gear connections, which makes sense. And using that multiplier, you can calculate the gear ratios for an array of gears with the same ratio each, or between each other. And as a result, what you can do is use a set of gears to increase either the speed or the torque outputted in a way that is more practical. For example, you may not be able to you definitely will not be able to just scale up your gears as much as physically possible in a realistic mechanism, or such as a robot, right? There are size limitations. So instead of doing one gear to get all the force you need, you increment it by having multiple sets of gears. And this can work even better when you have other gear mechanisms like worm gears, which can transfer the axis of rotation. Therefore, you can compact it on, kind of fold the rotation on top of itself. And what that does is it prevents it from taking up too much space, which on a robot is very useful. Although realistically, you're not going to be needing that much torque or speed in an FTC bot, but it is there if you need it. So there's that, and I think that should be it for this video, guys. Alright everyone, thank you so much for watching this quick video from 5795. I'm Omoza. Be sure to like and subscribe and share this video too, to make sure that everyone can get educated on STEM, and look forward to seeing you in the STEM community. Have a good day and keep on learning. Bye.